Okay.
Sir, I have written something in the chat.
You've written something in the chat box. Okay. How is the idea of output voltage leading the input voltage consistent with causality? Or is this a feature of only everlasting pure sinusoidal signal? Okay. Is this question clear to everybody? This actually is a pretty important question, and it should be on everybody's chat box. How is the idea of the output voltage leading the input voltage consistent with causality? This, of course, has to do with the fact that depending on the circuit configuration, when you're dealing with an AC circuit, there are situations where there is a phase difference between the output and the input. So basically, you have something like VO. Okay, let me just start presenting so that you can. Okay, let me switch off my camera. That will hit the bandwidth a bit. Anyway. Okay, so I hope this is visible now. And the copy should be visible now to everybody, right? Let me just expand this a bit. So the idea was you have VI, which is some voltage sine omega t plus phi 0, and VO, which is some other voltage. Let's say let's not call, okay, let's call this VI 0, and let's call this VO 0. Sine or cosine, doesn't matter. We did use cosine, but anyway. So in a typical AC circuit, this is what happens. You have an input voltage which has an amplitude and a time dependence, an output voltage which also has its own amplitude and its own time dependence. And the time dependence in both cases is sinusoidal, but there could typically be a phase difference. So it could be either sine omega t plus phi 0 or cos omega t plus phi 0. That's really the same function, just shifted in the time origin a bit. But there's also this extra delta phase shift. Now, the idea is if delta is positive, then output leads the input. And if delta is negative, then it lags behind. Of course, what does it mean when you say output leads the input? Now, this is something which, frankly, I found people not being able to explain very well when asked directly in a Viva, for example. Mathematically, it's fine, but what does it really mean when you say output leads the input? And the answer to that is that for the output, things happen earlier than it's happening in the input. When I say things, I mean something like, say, a sinusoidal function reaches a peak. So Vi reaches a peak. When does it reach a peak? When omega t plus phi 0 reaches, say, pi by 2. Because I'm talking about the sine function here. If this were a cosine, if it were the cosine function, I would have said it reaches a peak when omega t plus phi 0 reaches 0 or 2 pi or stuff like that. Anyway, for the specifically for the sine function that we have written down, Vi will reach a peak when sine omega t plus phi 0 is pi by 2, let's say. But VO will reach a peak when omega t plus phi 0 plus delta, this quantity is pi by 2, which means that the t needed for VO to reach a peak is actually less than the time needed for Vi to reach a peak. In other words, the input reaches its peak earlier than the output does. Now, Shayan's question is this consistent with causality? If you think of the input as causing the output, which is essentially what you always do, then isn't there something wrong here? How can the output reach a peak before the input does? But of course, the answer to this is also in his comment, because this is a feature only of everlasting pure sinusoidal signals. Of course, One thing you have to realize is the moment we say something like sine omega t plus phi 0, that's not really a very perfect description of what a real signal is like. A real signal has to start somewhere. Okay, so using sinusoids, or what we usually do is use the corresponding complex exponentials, which simplifies the calculation a lot and leads to all these concepts of complex impedance and so on. All of this presupposes that the signal has been present forever since the beginning of time. Forget about Big Bang and anything. And as a result, there the causality issue is not even a point, because the input has been there forever, so has the output. So input coming before the output or after the output doesn't really make much sense. Of course, if you really want to check the behavior of a signal which has started at a given time, then you cannot really describe it by Vi equals sine omega t plus phi 0. Even if it's sinusoidal, say if you are talking about a causal situation, when say the whole thing has started at say some time, let's say t equal to 0, then the actual signal should be something like this, where this theta t, not delta t, where theta is a so-called step function. 1 when t is positive, 0 when t is negative. So that's the actual input, not this. The full input has an extra theta t factor, which tells you that the voltage only starts after t equal to 0. Before t equal to 0, there was no voltage. Now, if you take this into account, the trouble is the moment you take this, then going to the complex exponential and using differentiation and all those nice tricks, they really start failing. Okay? So the way you would actually handle that is using Laplace transform properly, because Laplace transform takes into account the fact that the signal starts somewhere and the integral is only from 0 to infinity, not from minus infinity to plus infinity. Or you could simply say that fine, there would be something happening at the beginning, you would just ignore that and we are only looking at the steady state a long time afterwards. So the result that we have, that the output leads the input or lacks the input depending on your circuit, that actually is a result about the steady state, not really about what is actually happening in real time immediately. So the fact that the output reaches a peak before the input does not violate the fact that the cause must come before the effect. But the cause was, of course, switching on the circuit and switching on Vi. That produces effects only afterwards. What you see here of output leading or lagging behind the input, that only is something which you see long time after the whole thing has been set up, after all the initial transients have died down and so on. So, short answer, no violation of causality. But why not? Because either you say that the signal has been there forever, so causality is not an issue, or even if the signal has started somewhere, this form only is the correct behavior after a long time. And so now the input reaching a peak before the output or after the output doesn't really make any difference. At least not to causality. Okay, are there any further questions on this? Or anything else? There was a comment in the discussion box, a nice comment, which was for two-port networks. We have 4 variables, that is 2 voltages, 2 currents. Now 2 of them are taken to be independent. Which 2 that dictates which particular kind of circuit you are dealing with? So the question that was raised was, why not say V1, I1? Why not 2 input parameters, or why not V2, I2? Now the answer to that has been discussed. You had already discussed the answers in the discussion forum. I just added a bit of clarification after the fact, although that was just simply clarifying or putting together whatever had already been said, not really anything new. But the basic idea was there are two problems with this, or actually there are three problems with this. Uh, the most important problem is if you take V1 and I1 as independent, that sort of flies in the face of what we expect, right? After all, you do expect the input voltage. You do not really expect to be able to change the input voltage completely independent of the input current. So at an operational level, there's a problem with that. But at the end, what happens is if you really did this, then what you would end up with is something like this. You will get small v2 and small I2 as functions, as linear combinations of small v1 and small I1. I'm not really going any further in the explanation here, because I'm pretty sure anybody who has seen the derivation should be able to understand that these are the partial, here the questions are the partial derivatives. And maybe I need some name for this. Let's say eta 1 1, eta 1, eta 2. Now the trouble is eta 2 1 may not look nice because they are both 2 1. Well, let's say eta VV, eta VI, eta IV, eta II. 4 parameters which I've just invented these names because people usually don't have names for these things except in one condition. And the problem is, a set of equations like this would be impossible to implement as a circuit equivalent rather easily, because you have voltage and current both being specified in terms of controlled voltages and currents. Okay. Now this would be rather difficult, not difficult, this would really be in general impossible to implement as a circuit. And implementation as a circuit is nice because then you can also keep on using various circuit theorems. So that's one thing. So there are 2 points against this. One is treating the input as input voltage as independent of the input current. Even though mathematically it might still be okay, at least physically is something we should really not try to do. And secondly, if I did this, I would end up with Taylor series equations, just like in the other cases. But here the Taylor series equation would say voltage and current of the same port are being controlled by voltage and currents of the other ports. And just think about it, it will be very difficult, if not impossible, to actually implement both equations together in the form of a circuit. That doesn't mean that the equations are wrong, it just means a simple circuit implementation is not there. Well, there is one situation where this is used, as was pointed out in the discussion forum by one of you. The idea is, and these are called ABCD parameters. In fact, typically we will use V2, I2 as independent, and then you write V1 as A V2 plus B I2, and I1 as C V2 plus D I2. That's where the name ABCD parameters come from. For want of a better name, you can imagine that the only reason why this has such an unimaginative name is because it's not really used very much. There's one situation where this is used, is when you try to describe transmission lines which carry power, for example, from the power station to your end. And the reason why you use these parameters for transmission lines is rather simple. If you think about it a bit, all the other parameters that we have talked about, Z parameters, Y, H, all of them need you to control both the input and the output. Okay? So either you take the input short, output open, and so on. At the same time, suppose in the Z parameters you are trying to measure Z11 or Zi. That's V1 by I1, small v1 by small I1, of course. Small v1 by small I1 as small I2 equals 0. So you have to set a small I2 equal to 0 by shorting out the output, AC shorting out the output, and connect the current source to the input so that you can drive a current through it, known current through it, and measure the voltage at the input. So in a way, you have to have access to both the input and the output simultaneously. Now that's possible if your circuit is in a black box sitting in front of you in a table, let's say, and you want to experimentally measure stuff. You can in principle do it. In practice, you never put a short across a pair of terminals which is sticking out of something, because that would be potentially risky. But you can at least imagine doing that, and if you are not putting in a short, you can always put in some resistance and vary the resistance and see how the currents are changing. This is where you have both access to both the input and the output. The trouble is, for transmission lines, for example, things which stretch from the power station to your home, a description where you have access to both the input and the output and you can control both of them together is really not a convenient one. It's much more convenient to try to describe it by doing experiments, say, only at the output end or only at the input end. Which is why transmission lines typically use this kind of parameterization where V1, I1 or V2, I2 are taken to be independent. Not very convenient, but after all, you get mathematical equations and then use the mathematical equations. You can't translate them to very convenient circuit implementations, but that doesn't matter. You just use them as equations. Okay? So ultimately, whatever is allowed by the mathematics is used. And the other important question is, why do we need Z parameters, Y parameters, H parameters, all of them? Why not just learn one and simply forget about the others? Well, one answer is simply because they're there. You need to learn whatever is available. But more importantly, there are situations where one set of parameters may be more convenient to use than the other set. And a typical situation occurs in the cases where, say, say out of the 4 H parameters, 2 of them are very small. If that happens, then you can ignore them and you get a much simpler set of equations, much simpler set of equivalent circuits if you are using the H parameters. Now, since the Z and H parameters are related to each other, you can easily work out that even if, say, 2 of the H parameters were very small, it might so happen that all 4 Z parameters are large. It usually will happen that all 4 Z parameters are large and close to each other. So you can't ignore any one of them with respect to the other. Whereas 2 of the H parameters may be very small, 2 of them may be much larger. So in such situations, using the H parameters allow you to make approximations which are very useful and which sometimes may help you to handle very much more complicated circuits than you would otherwise be able to handle. So although mathematically all of these Z, Y, H are all equivalent, in practice one may turn out to be much more convenient than the other. Okay. Anything further? None. So now I have questions for you, although okay, this is not a quiz as yet, so don't worry about that. But there will be, by the way, these classes will also have quizzes where I ask questions to people by sort of arbitrarily referring to, okay, there is one thing for 2-port networks. We've assumed that the currents flowing in and out of each port respectively are equal. When did we do this? Oh, okay, Calvin, I think I am not sure whether this is your question, but I think your language is slightly problematic. You said in and out of 2 ports are equal. Now this is 1 port. Okay, this is one thing. This is the other. 1 port is 2 terminals, right? And we never assumed that the currents going in at these 2 ports are equal to each other. That we definitely did not.
So
okay.
I mean the 2
terminals in 1 port, right?
Yeah.
So you're asking what happens if there's a current source connected here. So what we assume was the current going in here is the same as the current coming out of this. Actually, we did not assume that there. That's why I kept on saying current going in at the upper port, right? This is the scenario. We always assume this, that when I1 goes in here, I1 comes out here. Okay. So you are asking, what if there's a current source here which will add to the current? I guess we already answered that question the last day. Current sources or voltage sources do not add to the current. They can't, or voltage. They can't add to sources, don't add to currents. Currents are really charge carriers which are moving in a wire. The job of a source essentially is to make the current or the charge carriers climb a potential barrier which they otherwise wouldn't have been able to cover. Say if this had been a voltage source here instead of a current source, the positive charges, I'm assuming positive charge carriers, although you all know it's negative charge, the positive charges would enter into the negative terminal, which is fine. You would say negative terminal attracts the positive charges, so that's not a problem. But then somehow they will have to get to the positive end. And getting to the positive end takes energy. The job of the power source, be it a voltage source or be it a current source, is to provide that energy. The energy for the charges to go on and complete the circuit. Okay. It's not their job to produce extra current. Whatever current comes in one end, same current goes out in the other. Always. Be it a battery, be it a current source. The difference between a battery and a current source is not in the fact that one produces extra voltage and the other produces extra current. The difference simply is that for a battery, the voltage between the two ends is sort of almost fixed by the battery itself, by whatever chemical processes or whatever goes on inside the battery. I say almost fixed because for an ideal battery, it would have been fixed. For a real battery, there are other processes which actually decrease the voltage depending on increasing current and so on, which is why a voltage source is always modeled really. A real voltage source is always modeled with an ideal voltage source in series with a resistance. That's just a Thevenin equivalent. Similarly, a current source is always modeled with an ideal current source in parallel with an admittance. Right? What is more important is the distinction between the two sources is a voltage source maintains a nearly constant voltage difference between its two ends. A current source maintains a nearly constant current going through it. But it's not as if more current goes in one end and goes out the other. In either case. Okay. Now, of course, it's possible that here instead of a single current source, you might put something more. After all, what do you do outside your two-port network? Your black box, something happens inside that. Then you have two terminals sticking out. What you do to those two terminals is entirely up to you. You can connect a whole mess of stuff, right? And the current can branch in various ways. But ultimately, whatever current goes out here has to come in because that's nothing but Kirchhoff's current law, the law of conservation of charge. Now, there's only one very important thing. None of these allow accumulation of charges. Okay. At least not in the long run. And not in the steady state, definitely. And that is why whatever current comes out here has to go in another end. So, language-wise, let's make this very clear. This is one port, this is the other. Two terminals make a port. And currents, when I say I1 current goes in here, I1 comes out here. Has to be because that's exactly what Kirchhoff's current law would be. Voltage sources or current sources do not change that. Okay. By the way, I've already uploaded the couple of videos for this week, but okay. Could you tell us how current control sources work? Also, is it possible to represent current control sources as conventional, as in what we have studied till now, circuit elements? The answer is no. No to both of them. You cannot relate or cannot represent a current control source as by when you say conventional, I assume you mean by terms of some resistances or voltage sources or battery or current sources. Even current sources are new perhaps to most of you, but they're sort of similar to voltage sources. But I'm assuming what you mean here is that in terms of some voltage sources and resistances, can you describe a controlled current source? The answer is no. For the simple reason that all these sources are local in nature. That is, a current somewhere causes a voltage drop there. So even if you move away from resistances and think of capacitors or inductors, they have non-local effects in time, in the sense that inductor does not, the voltage drop across an inductor does not depend on what is the current at this instant, but depends on the current in neighboring instances, how the current changes. Also, voltage drop across a capacitor depends not only on what is the current now, but also what the current was in the past. The current accumulated together to produce a charge difference leading to the voltage, right? So these are non-local in time, unlike the Ohm's law for resistances, which is current now is proportional to voltage now. For the capacitor or for the inductor, there is a time factor where there is a spread in time. However, they are still local in space. That is, voltage drop across the inductor is dependent on the current flowing through that inductor, how that current changes with time and so on, but not on the current somewhere else, right? Voltage drop across say a capacitor again depends on the current that has flown into the capacitor from some past time till now, but not on a current somewhere else. Voltage drop across the resistance, of course, is simply dependent on the current flowing right now, but again here, not somewhere else. Okay, so when you say current controlled voltage source is there, that means, or current controlled current source, you mean current somewhere else is controlling a current here. Okay, now why do you have such a thing? The answer is it's an effective circuit. Remember, all we are saying, just remember we did this for the Wheatstone bridge also, right? And we found current controlled voltage sources. We found Z12, Z21, all these numbers. But the real point was the whole thing was connected together, so one current did affect the other thing. The current flowing in the input did affect the output voltage because the whole thing was connected inside. But instead of this whole mess of stuff inside, we can effectively think of them as much more simple circuits. So they're not theoretical concepts in the sense that when you say it's a theoretical concept, now that of course is a matter of language. When you say it is a theoretical concept, do you mean that it does not exist? Can I produce a current control voltage source? I can actually produce current control voltage sources. We will design several current control voltage sources or voltage control current sources in the course of this course itself. Once we study op-amps, we will learn how to use op-amps to produce voltage controlled or current control sources. So these are not theoretical abstractions of more practical devices. They are perfectly practically available. Okay, but the point really is that they are typically not something you can make out of resistances, conductance, capacitances, or inductances. But in a sense, they are mostly theoretical abstractions. For example, when we talk of something like a transistor, you have already perhaps learned a bit about the transistor in your high school, and you know that there is something called a base, something called an emitter, right? And something called a collector. Is that okay?
Yes, sir.
So you also know that if you send a current through the base, and that actually, or rather if you send a current through the emitter, that's really more physical, that controls the amount of current which goes through the collector. So you have a current, you can model this. This is a real effect. You're essentially pushing in current somewhere, you're getting current somewhere. A part of that is coming out somewhere else, right? So this is a very real effect. Okay. So what you are doing here is you're modeling that real physical effect by just a simpler model of just a current source. Instead of the entire physics which goes on inside a transistor, you end up with two simple control sources. Okay, now I have another question. So Rajrupa has a question. I will discuss that. But before that, is there anything else that about this? You will see plenty of voltage control, current control, current sources in action when we talk of, say, transistor circuits. And then you will see physically why do you have a source like this. Okay, but if you are asking me, can you make such a circuit using just resistances, capacitances, inductances? The answer is no. But we can make such circuits despite that. We can ensure that the output voltage of a circuit is proportional to the input current somewhere, which is, of course, something you always know, right? And that's what an current to voltage amplifier would be like. And that would be modeled by there would be a complicated bunch of things inside, but a very simple model of that will be a current control voltage source. Okay. Now, I guess before we go to anything else, I think we should clarify one thing. And this is something which almost everybody knows, and at least they think they know. But can anybody tell me what exactly is an equivalent circuit? When I say something as simple as this, suppose I have two resistances in series, and that's equivalent to a single resistance R1 plus R2. Can anybody tell me exactly what it means when I say R1 plus R2 is equivalent to R1 and R2 in series? What is the exact meaning of this? It can be replaced by this. Physics remains the same. Both of them are correct partially. For the same potential difference across the circuit, the same current flows. Again, correct, but only partially.
Sir, for the same given inputs, they will have the same outputs.
That's essentially the same thing, right? Or everybody is saying the same thing. Well, the really important thing about an effective circuit or equivalent circuit is if this thing appears anywhere in a circuit, not just in isolation, all these statements that you're making, same potential difference across same current flows, etc., these are correct, but they sort of imply that you just have R1 and R2 in series, and then you put a potential difference across it. Actually, this statement can be generalized to other cases as well. But strictly speaking, what it means is if this combination occurred in a circuit somewhere, if you were to replace this by this, then the currents and voltages everywhere else stays the same. Everywhere else is critical. Because, for example, the voltages here does not stay the same after you replace. The voltage difference across the two ends, which you should realize is actually outside this, right? Your R1, R2 combination speaks to the outside world through its two ends. So if you have understood the black box concept, you can think of putting this whole thing in a black box, two ends sticking out. If I were to change the inside of the black box and replace them by just this single resistance, by looking at it from the outside, I should not be able to tell the difference. That's what an equivalent circuit really means. When I have a star delta transform, for example, and that was actually the last question on the second problem sheet, some of you have given the correct answer almost, or some of you have given nearly perfectly the correct answer, but that's really a rarity. The star delta transformation, if you look at any book, the way it works is this. You just calculate the potential, the effective resistance between these two ends. Here, let's call them A, B, C in this and A, B, C here. And you simply say, okay, if I try to find the effective resistance, and let's label these. This is RC, RA, RB. A standard rule for triangle edge denomination, right? The edge is labeled with the opposite vertex. The small RA, small RB, small RC. The standard proof that is given is if you look at, say, these two terminals, then what is the effective resistance? It's actually RC in parallel with RA plus RB. But that's the case for the delta. For the star, you must have the same, so this must be equal to small RA plus small RB. In this way, you write down three equations, and you solve the three equations together, and you get the values of RA, RB, RC. Straightforward. The real problem is that this is fine if you assume that the delta and the star were alone in the world. There was nothing else connected to them. If you are claiming that this is equivalent to this, what you're really saying is, no matter what I connect to this, whatever I connect here, whatever I connect here, whatever I connect here, if I do the same connections here, here, and here, as far as the outside world is concerned, voltages and currents will stay the same. Okay. Now the proof, that is the calculation that is usually done to derive the values of the transformation, star delta transformation, assumes one very critical thing. It assumes that there exists for every delta really a star, or for every star a delta. Once you make that assumption, that no matter what you connect to ABC, the star and the delta will behave the same way, or really they will look the same from the outside world. Now comes the important thing. If that is true, then of course they will also behave the same way if you were to connect nothing else. So suppose you did not connect anything to C and try to measure the effective resistance between A and B, you should get the same result in both cases. And then this equation is perfectly correct. Now, I'm not saying this equation is wrong. All I'm saying is this presupposes that there is a star delta effective circuit. If you did not know that beforehand, if you did not have a theorem which somehow told you that you can change a delta into a star and vice versa, then frankly, this will really tell you nothing. This will tell you that, okay, fine, if I did not connect anything to C, then maybe these two things will work the same way. But equivalent circuits are not that. Equivalent circuits mean that no matter what you connect outside, the system will behave the same way. Okay. So when I say why is the outside part important, something as simple as the R1 R2 series combination. There is a voltage division inside the series combination that no longer happens when you replace it by a single resistance, right? You don't have two resistances, so you don't get a potential drop across one resistance and another drop across the other resistance. So the voltages and currents inside the black box might very well change. What happens is things outside the black box will not change. That is exactly what this equivalent circuit thing means. So as far as, say, a two-port network is concerned, for example, if you replace the two-port network by its two-port equivalent, voltages and currents in the outside world will not change. Inside, of course, something very messy has happened. Early inside you had maybe a transistor which was taking in a current from one side and pushing it a fraction of that in the other, and so on. All that has gone away. You just have a input loop and an output loop. Of course, it's a much simpler situation as far as the equivalent circuit is concerned. You may feel a bit queasy about using control sources, and it may make it seem a bit more difficult, but it's really a much easier situation now, right? You could have had something very messy going on inside, which you don't have any longer. But what is important is you're not claiming that voltages and currents inside the black box stay the same after you replace it by an equivalent circuit. Something happened inside, something very complicated may have happened inside. You're modeling it with these two-port networks. That is the critical thing to think about. Okay. So those models naturally lead to controlled sources. And if you want to describe something very complicated in much more simpler terms, just by an input loop and an output loop, then the price you have to pay is control sources. Okay, now let me come to Rajrupa's question. She asked, when we work with complex potential and currents, only a real part has a physical manifestation. Shouldn't the amplitude of the complex number instead give a better picture? Actually, no. If you think about it a bit, suppose the reason why the real part and imaginary part both work is that this, say, V0R plus J V0I, this is the situation, right? A complex number has a real part and an imaginary part. Now, any of the circuits that we deal with, all the circuits that we use, some circuits which have terms like this, or whatever, all of these are essentially linear terms. This is important. Non-linearities will make life a lot more difficult. You have linear terms, number one. And all these terms are real terms. There is no complex quantity anywhere in your actual equations. What that means is that if a complex function satisfies whatever differential equation or algebraic equation you have written down, its real part and imaginary part would both separately satisfy the equation. which, since the equations are what actually describes your physical system, is either the real part or the complex part or the imaginary part, which are actually the physical manifestations. Strictly speaking, it's the other way around. We know that the input voltage Vi is some constant into cosine omega t plus phi. Let's say this is what you start with. It's not the real part of a complex number. This cosine function is really what describes the input function. Okay. Now you might say, of course, all input functions are not cosines, but then I would counter that by saying, okay, if it's a periodic input function, then it will be a sum of lots of cosines or sines. And by the way, cosines and sines are all the same. All you have to do is change the phi. So because of Fourier series, if you know how cosines behave, you essentially know how the circuit behaves for all signals. Now this is what you really have. Okay. It's not as if you had a complex function whose real part or imaginary part or magnitude you can choose. This is what you have. This is where you start. Now what you do is you write this as a tilde e to the power j omega t, real part of where a tilde is a to the j phi. Now this is a mathematical truth, right? That if you write a cos omega t plus phi as a real part of a tilde to the j omega t, that's just mathematics. There's no physics here. Okay. All we are saying is, instead of doing your calculations with a cos omega t plus phi, you can happily do the calculations with a tilde to the j omega t, as long as you're doing nothing non-linear. And the reason why you would prefer doing it with a tilde to the j omega t has no physics in it, but mathematics in it. Exponentials are easier to handle when differentiation and integration are concerned. Okay, that's the only reason why you're going in for this. You could perfectly well work throughout with cosine omega t plus phi, solve the differential equations that come and so on. You could do that, except that it would be much more difficult to do mathematically. Exponentials are much easier to handle in a scenario where there are derivatives. And that's the only reason why you like using this. Now the magnitude will be a bad thing to use. Why? Because the magnitude or the square of the magnitude are both non-linear combination of both sides, right? So even if a complex function satisfies an equation, its magnitude definitely will not satisfy the same equation. By the way, for the wave function, for example, the wave function obeys the Schrodinger equation. The modular square of the wave function, the probability density, of course, does not obey the Schrodinger equation. It obeys an entirely different equation. Okay, and it in fact doesn't obey an equation on its own. It and the phase together obeys an equivalent equation. So now one word of warning, which is very important, is that you should never really forget that no matter how many complex functions you use, at least when you're using complex functions in electricity, electronics, or electromagnetism, but almost everything other than, say, quantum mechanics, almost everywhere, what you really mean is that you have a function which is like this, and you're representing it as a real part of something like this. And very often, because you can actually work with just the complex function and at the end take the real part, you very often just forget about the real part for the time being. You happily work with the complex function and draw answers at the end from the complex functions directly. So, which is why when you have something like VO is, say VI is a tilde to the j omega t, and VO works out to be b tilde to the j omega t, then VO by VI, a tilde by b tilde. This is the relationship between, this is actually not VI, this is VI tilde, this is VO tilde, the complex value representatives. However, because we often work with this, we don't say that these are the complex functions which represent the real functions. We just say VI tilde is, or VI is this, and happily calculate the whole thing. And then we realize that if this is r into something like r into the I theta, which is this of course is a complex number, so it can be written down like this, then you can draw conclusions from the for the actual amplitude of VO by VI ratio and the actual phase difference between VO by VI simply from here. Why? Because once you have this, it really means, this of course means VO, the actual voltage, is B cos omega t plus whatever the phase of B is, so phi B. Whereas VI is A cos omega t plus phi A. So what I really want is A by B, this ratio, which is the ratio of the two amplitudes. And what we also want is phi B minus phi A, which is the phase difference between the two signals. This is what I really want. Okay. However, you can see that if A tilde by B tilde, A tilde is A to the power I phi A, B tilde is B to the I phi B. So this ratio is simply A by B e to the I phi A minus phi B. Okay, I wrote the whole thing wrong. This should be B tilde by A tilde, of course, because I written VO by VI, VO tilde by VI tilde. And then what I want really is B by A, phi B minus phi A. So, sorry, B tilde by A tilde is B to the I phi B by A to the I phi A. So, it's a simple matter of algebra to show that this is what comes out. So, R, the ratio between the two voltages, the amplitudes of the two voltages, is also the same as B by A, of course, but that's also what you get as a magnitude of B tilde by A tilde. So if you calculate the complex voltages directly and take the ratio, you get a complex number. That complex number has in it both the amplitude ratio for the real waves and the phase difference of the real waves, both information in one piece. So it's easy to, you don't have to calculate the amplitude separately and the phase separately. It all comes out of one single simple calculation. Okay. So using exponentials makes calculations very easy, but doesn't mean that the real things are the complex exponentials. That's one thing. And the other very, very important thing is this. Say, for the capacitor, for example, you want the capacitor energy. That's half CV square, right? Now, if V is V tilde e to the j omega t, if you plug that directly here, C V tilde square or V tilde 0 square, 2j omega t, and then try taking the real part, because after all the energy has to be real, you end up with half C V0 square cosine twice omega t plus twice delta or something. This is completely wrong. Why is this completely wrong? Because taking the real part after squaring is not the same thing as taking the real part after squaring is not the same thing as taking the square of the real part, right? Squaring is not a linear operation, and the moment you have nonlinear things like that, calculations of energy and say power and stuff like that, then this goes wrong. Okay. Now what do you do in such cases? You can do one of two things. You can either always remember that whenever you're calculating things like energy stored in the capacitor or power dissipated in the resistance and stuff like that, always remember first to take the real part, then calculate the power or the energy or whatever you want. That's one way of doing it. And there's another way. The other way is you can actually, at least as long as you're dealing with average power, average energy, there's a way to rewrite the expressions in such a way that even your complex functions complex exponentials can be directly used. Not in the form that you would expect, but in a slightly different form. For example, let me just illustrate that. That's an important thing. Suppose the voltage somewhere is this V0 cosine omega t plus phi, and the current in the same region is some I0. You all know this, I'm pretty sure. Phi plus some delta. The current and the voltage may have a phase difference. Now, what is the power here? P of t. Of course, the complex versions of this would be V0 tilde e to the j omega t, where the V0 tilde is V0 e to the j phi, and this would be e to the I0 tilde, where I0 tilde is I0 e to the j phi plus delta. So I0 tilde is I0 by j phi plus delta, the entire initial phase of the current, and V0 tilde is V0 e to the j phi. Now, what is the power? You can think of the power as, of course, voltage times current. But which one do you multiply? Do you multiply these two? Of course, you don't. You multiply these two. So the actual instantaneous current is, of course, V0 I0 into cosine omega t plus phi into cosine omega t plus phi plus delta. Now, this is exactly correct. However, very often we are interested not in the instantaneous value of the power, but in the average power that is delivered over a cycle. Why over a cycle? Because if you look at many cycles, or look at this for a long time, then a long time interval will fit some integer number of cycles and some fractional bit after that. But the contribution essentially will be dominated by the integer number of cycles, and each cycle contributes the same amount because the whole thing is periodic. And so you just take the total amount. The average power over a long interval is the same effectively as the average power over one cycle. If it's an integer number of cycles, then it's exactly the same. But even if it's not an integer number of cycles, if it's a very long time interval, then the extra contribution which comes from a small fraction of a cycle sitting outside will essentially be negligible. So you average this over a cycle, and this is what you really want to calculate. And I hope everybody knows what the answer to that is. What is the answer to this? If you average this over one complete cycle?
V0 I0 by 2 into cos delta.
Right, it's V0 I0 into cos delta. Okay, and this cos delta is what is called the power factor. Of course, how do you do this? You just simply integrate this over one complete cycle and then divide by the length of the cycle. That is, you integrate this from small t equals 0 to small t equals 0 to 2 pi by omega and divide by 2 pi by omega, and this is what comes out. But how do you get this result directly? By looking at this, the V0 tilde I0 tilde, the complex voltages, exponentials. Can of course say I start with the complex exponentials, but I will, the moment I go to nonlinear things like calculation of power, I will stop doing that. I will just take the real part, then integrate, multiply and integrate and stuff like that. But what you could also do is this: if you multiplied V0 tilde by I0 tilde, it will not work, right? But what will work is this: if you multiply the V tilde, not V0, V tilde with I tilde, conjugate. Why conjugate? If you do the conjugate, then e to the j omega t into the minus j omega t will cancel. E to the j phi into the minus j phi will also cancel. It will just be left with e to the j delta. Right? It's either V star I V star I V tilde star I tilde or V tilde I tilde star. Take this, take the real part, halve it. Because the moment you do this, V tilde I tilde star, it is a j omega t plus phi cancels out because of the conjugation. If the j delta is the only thing, either it is a j delta or the minus j delta survives. In both cases, if you take the real part, you do get V0 I0 cos delta, and you have throw in a half from outside. Okay, so this is the formula which you would have to use for the power if you are using complex exponential voltages and don't want to give up on that. Okay. Now later on, I don't know whether it's later on or even earlier, you may have already heard of pointing vector, right?
Yes, sir.
And when you calculate pointing vector, you calculate E cross H with some extra factors, right? But when you're talking of waves, you deal with E cross H with being complex vectors simply because, again, you take the real part. The waves are easier to describe in terms of complex exponentials. But then you would see that the formula that you use is E cross H star, real part of that, by 2. Same reason as this, basically. All I'm saying is you can mimic the calculation that you do, that you should really do. Take the actual instantaneous voltage, instantaneous current, multiply average by, you can shortcut the whole process by simply multiplying the voltage by the conjugate of the current, taking the real part and dividing by 2. That does the job just as well. Okay. So the point is, if you want to do nonlinear things, if you know the shortcut to use, you can use that. But if you don't, you have to take the real part first and work it out. It's always a real part. That is a real calculation always. Okay. Now, let me just quickly wrap up because I'm already beyond time. That is beyond time, meaning I should have left you go 3 minutes earlier. Just one question to all of you. I'm going to start with diodes next week. There will be one small lecture on the rest of the AC circuits, but that will be maybe tomorrow, today, or tomorrow or day after. That's really not a great deal. It's just a follow-up of whatever we had earlier. But we will start with diodes the next day. So do I assume that everybody here understands intrinsic, extrinsic semiconductors and stuff like that? Yes? No, I'm not saying that whether you understand that in the level of some deep physics. The deep physics is beyond the scope of this course. For that, you will have to do a full-fledged solid-state physics course next year. But at the if I say something is an intrinsic semiconductor or something which has been doped with a pentavalent atom and hence has extra electrons, would that be familiar or would that need an explanation? Yes? I need an answer from you.
Sir, it's better to ask the other way question.
What is the other way question?
Like, who doesn't know it?
No, that's fine. That's exactly what I said. Is there anybody that, well, whenever I say something like this, it always means this, that if you do not know this already, please say. Do you understand this? The answer is no. Nobody, by the way, none of you actually understand what goes on in a hole or an electron or whatever. Let me guarantee that for you, because that requires rather high-end quantum mechanics, which you have not even come close to understanding. Okay. But at an operational level, if somebody says a hole and electron recombine, and now you have no charge carriers left, I hope everybody understands what that means. I'm just trying to judge where I would start my explanation on diodes. You have already done something about diodes in higher secondary, I guess. But maybe we will talk a bit more about how they work. 3 years ago, a brush up would be nice. Okay. I will just assume that everybody knows what intrinsic and extrinsic semiconductors are. If you don't know that, please read up in between. Because frankly, otherwise it will take way too long. But I will start with the diode PN junction and how the PN junction works. There's one more question. Are the terms diffusion current and drift current familiar to anybody? Diffusion, drift. Yes?
Yes.
So is it known for anybody? Diffusion current and drift current? Nobody is saying something, so I'm assuming everybody knows at least the words. What they mean is a deep thing, but again, we'll talk about that in the next, not the next, but the next to next video. Okay, bye for today. I'm already out beyond time. Chalo, let me stop the recording.